Okay, so we're going to do a problem with a projectile that's launched at an angle. And in this case, we have a golf ball that's hit with an initial velocity of 52.5 meters per second at an angle of 42.0 degrees. Find the distance the golf ball will travel, ignoring air resistance and the effect of the dimples. So all that parentheses part means is that we just want to make physics simple. And it gets very complex. And if you're interested in knowing what the dimples do, I encourage you to look that up. It's actually really cool. But we're going to ignore that. So the first thing that you want to do is to figure out, what are they telling me? Well, we know that we have an initial velocity, which means starting velocity, at 52.5 meters per second. We also know that that is at an angle of 42 degrees. So that means that this velocity is not just in the x, it's not just in the y, it's a combination of the x and the y. So in order to figure out what my velocity is horizontally and vertically, you need to use your vector knowledge to set up a right triangle. So we have a launch angle of 42 degrees. And we have an initial velocity, which goes on my hypotenuse, of 52.5 meters per second. So now you can just drop your perpendicular. And we know that this side, since it's the x, the flat side is the x, we can label that Vix. And the vertical side is the initial velocity in the y direction, because it's up and down. So what that means is we want to figure out, how fast is this ball moving forward, how fast is it moving up. And I'm actually going to separate my page so that I can put my information for x and y on two different sides. So solving, since x is on the adjacent side to the angle, I'm going to use cosine. So Vi in the x direction is going to be 52.5, my initial velocity, cosine of my angle, 42 degrees. And so if you put that into your calculator, you end up getting that Vix is 39.0. The reason why I'm writing that 0.0 is because all of my stuff was given with 3 significant figures, so I want to keep that. In the y direction, V initial, we're going to use sine because it's the opposite side. So that's going to be 52.5 cosine of 42 degrees. And so that, if you put it in your calculator and use 3 significant figures, you get 35.1 meters per second. So checking the problem, they don't give us anything else, which means we have to figure out what's going on based on our assumptions. Well, one of our assumptions is that since we're ignoring air resistance, my acceleration in the x direction is 0. There's nothing that's stopping the ball. There's also nothing that's speeding it up. So it's just going to have an acceleration of 0. Well, if it's not speeding up or slowing down, that also means that my initial velocity is equal to my final velocity in the x direction. So however fast forward the ball is moving, it's going to continue at that speed the entire time. Also, I know that due to gravity, my acceleration in the y direction is negative 9.81 meters per second squared. Okay, so now we've kind of run out of the initial velocity and acceleration stuff, which should be really, really simple for us. So now I'm going to go through and think about what other assumptions might I have, and or what am I looking for. So I'm looking for the distance the golf ball will travel. So if I want to draw a diagram off to the side here, if this is my ground, got a thick line here. I imagine this is the ground and it's on a fairway, so I'm using green. And my golf ball is starting on a tee. I'm going to end up hitting it. It's going to follow a parabolic trajectory, which means it's going to look like a parabola or a curve. And eventually it's going to fall back to the ground. So if I start on the ground and end on the ground, that means that in the y direction, up and down, my displacement is 0 because it's starting and ending at the same place. So I'm actually going to add that to my assumptions over here, that delta y is going to be 0 meters, if I want to add my unit in there. The only other thing that I could know in the y direction would be maybe my final velocity, which I don't know anything about. There's no assumption about that. I also don't know the time that it takes for the ball to fall back to the ground. And so I'm missing time, I'm missing final velocity in the y direction, and I'm also missing delta x, which is what we want. Okay, so now I'm going to focus back in on the left-hand side, the horizontal direction. Before I go any further, I actually want to write down my equations because it helps me solve the problem, and these are the equations that you should know at this point. The four constant acceleration equations that we've talked about are displacement equals 1/2 vi plus vf. What that means is it's the average of the velocities times delta t. Another equation we know is that delta x, my displacement, is 1/2 acceleration delta t squared plus v initial times delta t. Then for final velocity, I know that it's acceleration times delta t plus v initial. Another equation for v final is v final squared equals v initial squared plus 2a delta x, not delta t, delta x. So one thing I want you guys to know about these equations is that delta x is standing for the displacement in one dimension, which means that delta x really could mean delta y if we're looking at the y direction. Well, okay, we're looking for delta x. If I look at these equations, there are two delta x equations, and really the last one also has delta x in it. But because acceleration is 0, all of those a parts disappear. So the only useful equation we get out of that is that delta x equals v initial in the x direction times delta t. Well, we're looking for delta x. We know v initial, and I also don't know delta t. So I really can't go anywhere. In order to go and find delta x, that means that I need to find delta t first. But because I have no other useful equations in the x direction, that means I need to look and see if there's an equation in the y direction that will help me find delta t first. Well, in the y direction, so far we have that initial velocity, we have acceleration, we have delta y. So we have three things, and we're looking for delta t. We learned in the first chapter that if you have three variables and you're looking for a fourth, that's enough. So looking at my equations, I need an equation with v initial, acceleration, delta y, and delta t in it. And that equation is the second one. So instead of writing delta x, I'm going to write delta y, because we're in the y direction, equals 1/2 acceleration delta t squared plus v initial, and this is in the y direction, delta t. So now I'm going to plug in everything I know. And I usually like to write the equation first to keep my head straight about what I'm plugging in where. So delta y is 0, 1/2 acceleration, I know it's negative 9.81 meters per second squared. To save space, I'm just going to write the number, delta t squared, plus v initial in the y direction, which we calculated as 35.1 meters per second, delta t. So if you notice, this is a quadratic equation. It's quadratic because we have a square on my variable delta t, and I have another delta t that's being added in addition to that. So in math class, you learned the quadratic formula, and some of you may have thought that you would never use it, but here we're going to use it in physics. So that formula, if you don't remember, is, I'm going to write it way down here to help us out. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And that gives us a solution for the variable. Now a, b, and c are the coefficients where a goes with the second power, b goes with the first power, and c is just a number by itself. So if we look at this 1/2 times negative 9.81, that's our a value. This 35.1 is our b value. And if you notice, there's no number being added at the end, so the c value is 0. So using our quadratic formula, delta t is equal to negative b, so negative 35.1, plus or minus square root of b squared, 35.1 squared, minus 4ac. Well, we just established that c was 0, so if c is 0, that 4ac term completely disappears. So it makes life simple for us. 2a, if I look at my a value, a is 1/2 negative 9.81. Well, if I multiply that by 2, the 2 and 1/2 cancel each other out, and so we're just left with negative 9.81. And if you didn't realize that and you figured out that this 1/2 negative 9.81 is negative 4.905, and then multiplied by 2, you've been like, whoa, there's that negative 9.81 again. Either way, you get the same answer. So now if you do this calculation, the square root of something squared, those cancel. So one of your terms is 0. You get delta t equals 0. Well, that's when we're hitting the ball, and we don't really care about that. So we're going to throw away that answer. And the other answer, you end up getting negative 70.2 over negative 9.81. And then calculating that using correct significant figures is 7.16 seconds. So we know that it takes 7 seconds approximately for the ball to follow this path and fall back down to the ground. So now that I have delta t, that was my short-term goal, I need to go back, plug it in up here to get delta x, which is what I was actually solving for. So delta x, the distance, is going to be equal to v initial, which we calculated in the x direction as 39.0, times 7.16 seconds. And so total, we get that the displacement in the x direction is 279 meters. That's my final answer. What that means is the golf ball will end up 279 meters down the fairway. So I hope this problem helped you figure out how to find the final distance of a projectile that's launched at an angle.